Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. I'm very pleased tonight to welcome Dr. Paul Butler, who is a staff scientist at the Carnegie Institute of Washington's Department of Terrestrial Magnetism. He received his PhD from the University of Maryland and has since won many honors, including the Henry Draper Medal of the National Academy of Science. He's a fellow of the American Academy of Arts and Sciences and Discovery Magazine's Space Scientist of 2003. But I think my favorite of all is that he was one of Newsweek's 100 Americans for the next century. And since this is the next century, we're very excited to have him. But mostly he is known as a co-discoverer of hundreds of planets around other stars, including Alpha Centauri Proxima, our closest stellar neighbor. So please join me in welcoming Dr. Paul Butler.
One of the really fun things about the field of extrasolar planets, first of all, when I got started, that was 30 years ago, there were no extrasolar planets. And if, in fact, you went to a science meeting and people asked you what you did, you couldn't say, I'm looking for planets around other stars, because you'd get a couple of responses. One, they'd laugh at you. Two, they'd move slowly away from you, like you're trying to pitch some new age religion, or maybe you smelled really bad or something. So all you could say is, I'm trying to measure Doppler velocities more precisely, and then that there were no extra questions after that. Things have changed dramatically in the last just 20 years now that extrasolar planets have actually been discovered. Back in those days, you'd discover a couple of planets and you get a huge amount of publicity. Now that there are thousands of planets known, we find things that we think are the coolest ever, and they hardly even make a blip on the publicity. But one of the really cool things about this whole field is it ties back to the actual origins of science. So if you can imagine going back, science is only 400 years old, so if you can imagine going back 500 years, you were literally living in the Dark Ages. If you got sick, you died. That was it, and there were no TV, no radio. Entertainment for most people was simply looking up at the night sky. And the night sky was extremely reassuring, because all the stars form these patterns, these constellations, and they keep the exact same pattern. You can't discern any motion over the course of a human lifetime. And they all circle around the Earth, rising in the east, setting in the west, and giving us this nice, wonderful pattern. And also, of course, implanting on us the notion that the Earth is the center of the universe, because as we look up, everything appears to be going around us. So one of the early problems that predates science, that led to science, is the problem of the motions of planets. The planets also move around us, or appear to, but the problem is, once every orbit or so, the planet will appear to, I'm getting stage directions here. Is this where I should stand? In the light. Okay. I need to be a Shakespearean actor on top of everything else. So once every orbit or so, a planet will appear to go backwards in its track. So we blew through that real fast, so we'll go do the exact same thing again. And when the planet appears to move backwards in its path, that's called retrograde motion. And there's a real problem with that, because the theories of the cosmology theory at that time said the Earth is the center of the universe and everything travels around the Earth. Everything in the heavens are perfect. There's only one perfect shape. It's a circle, and everything should just go around us in circles. But this thing has got this crazy loop. So people worked incredibly hard for a couple of thousand years to try to reconcile this. And they came up with this crazy idea called epicycles, where you imagine that the planet doesn't actually travel on the circle around the Earth. The planet travels in a circle around a point that is traveling in a circle around the Earth. And that by doing this, you can generate this sort of backward motion. The problem with this is that if you looked very carefully, say especially at Mars, this one simple epicycle didn't work. It didn't predict the motion terribly well. So what they then did was, where Mars is on that diagram, the big red dot, they put another epicycle and put Mars on a second circle around that. So now you had an epicycle inside of an epicycle, and that reproduced the data a little bit better, but not great. And over hundreds of years, with more and more observations, they kept adding more epicycles. And by the time the system collapsed, Mars was sitting on top of 56 epicycles. So pre-science, the very beginnings of science often are associated with Copernicus, who in 1530, on his deathbed, publishes a book in which he says, hey folks, maybe the Earth is just a planet and it goes around the sun. And so this is 1530. Probably not more than 1% of the people in Western Europe could read. So it's not exactly like this is going to be a top seller. And furthermore, it's probably written in Latin. Nonetheless, Copernicus was very aware of the fact that he was on very thin ice here with the powers that be, and he waited until he was on his deathbed before publication. So the nifty thing with Copernicus's theory is it very nicely explains this retrograde motion. Simply, the Earth is the green planet, and as it passes Mars, Mars appears to go backwards, and you get this retrograde motion, and you don't have circles within circles within circles. So this is just like if you're at a traffic light and a car goes by you and it appears everything is moving backwards. It's just from perspective. So over the next 50 years or so, this theory slowly picked up adherents. The few people who could read it and understand it, they loved the simplicity of it. And one of the, well, maybe the Carl Sagan of his day, Giordano Bruno, in 1584 publishes a book in which he expands upon the Copernicus notion, and he writes, there are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. The countless worlds in the universe are no worse and no less inhabited than our own Earth. So, you know, we think, well, so what? This is the premise of every Star Trek and Star Wars episode ever made, right? But in these days, this was dicey stuff to say. And this, along with other cutting edge things he did, ended up, well, let's just say it didn't end up so well for Bruno. So there are a handful of ways that extrasolar planets are found. The most obvious thing to do is direct imaging. You can imagine taking your telescope and pointing it at a nearby star and trying to see the teeny little planet next to it. The problem with that is that even a giant planet like Jupiter is about 1 billion times fainter than the host star. So you're looking for this thing that's 1 billion times fainter right next to this bright, brilliant, blinding thing, the star. And so this has historically been a huge problem. And there have now been a handful of giant planets around very young stars that have been found by direct imaging. But the sort of planets that we're all excited about, solar system analogs and Earths, those remain out of grasp. But it's the sort of thing that we're maybe on the cutting edge. In 20 years or so, maybe these things will start to be directly detected, which would be incredibly exciting. Then there's transits, which I'll show you a slide in just a moment. Microlensing, astrometry, and Doppler spectroscopy. I won't speak much about microlensing. With the others, I'll give at least a brief mention to. In transit spectroscopy, if you're very lucky and the line of sight between the Earth and the star is such that the planet actually crosses the face of the star, then once every orbit, as the planet crosses the star, it'll block some of the light from the star. So Jupiter has about 1% the surface area of the sun. So if a Jupiter-like planet goes in front of a sun-like star, it will decrease the light from the star by about 1%. So that's actually pretty easy to do with ground-based photometry. If you then want to do Earth-like planets, it's much harder, and you're now looking at changes in light at about 1 part in 10,000. And to do that, you go to space, which is why there was the original Kepler mission and why there's the upcoming TESS mission. The way that people have been looking for planets for most of the last century is astrometry. And what you do there is, as the planet orbits the star, it kicks the star into a small counter orbit. This is just Newton's third law. For every action, there's an equal and opposite reaction. So people have been taking photographs, literally going back 100 years now, taking photographs of nearby stars and trying to see stars that wobble relative to background stars. And Peter Van de Kamp famously found a couple of planets around Barnard's star in the 60s, even made the astronomy textbooks. Those are now widely discounted, but nonetheless, Van de Kamp was sort of a pioneer in this field in that he thought planets were common and that we should work really hard to try to detect them. And I believe he died in the year planets were discovered. He lived to be 100. The technique which found the first several hundred planets and continues to be instrumental in following up transit planets is Doppler spectroscopy. So Doppler spectroscopy is similar to astrometry in that you never see the planet itself. You see the gravitational effect that the planet has on the host star. So here, as the unseen planet orbits the star, for half of that orbit, the star is approaching an observer on the Earth, and the light is compressed by the Doppler effect, and astronomers call that a blue shift. And for the other half of the orbit, the star is receding from an observer on Earth, and the light gets stretched out. Astronomers call that a redshift. So you're looking for this very small effect of the light going back and forth. This is not bizarre. This is common everyday stuff. The highway patrol officer with his radar gun is doing exactly the same thing. He's sending out a radio wave of a known wavelength. If your car is moving, when it bounces off the car, it'll come back to him compressed, slightly shorter wavelength, and the amount by which it's compressed tells the officer how fast you're going. So you can see that this is a technique that can be used for both good or evil. This just sets the scale for where we're looking for planets. This is sort of a stand-in for the Milky Way, and I hate to tell everybody, but as far as the Earth is concerned, we're way, way, way out in the exurbs. We're nowhere near where the action is. The Doppler spectroscopy, astrometry, and direct imaging all only work or best work on the very nearest stars. So that teeny little pink dot in the middle, that star is within about 50 parsecs, or roughly 100, 150 light years. So on the cosmic scale, our very closest immediate neighbors. Transit searches typically work on stars that are about 1,000 parsecs away. That's that little blue circle. That little blue circle looks like it's really close to the center, but in terms of astronomical observations, just being that far away from us makes it incredibly difficult to follow up the stars. So at the heart of the Doppler technique is a high-resolution shell spectrometer. So historically, astronomers can take spectra. So a spectrometer is just basically a fancy prism. It just divides the light from the star into its component colors. And historically, astronomers could either take spectra of the entire optical wavelength range, but only at very low resolution. Or they could take very high-resolution spectra, but only over teeny, teeny, teeny pieces of the spectrum. What shells did when they were invented back in the 80s was they allowed both. You could get high resolution and full optical wavelength coverage. For spectroscopy, the telescope is just a light bucket. That's all it is. So the telescope gathers the light, and in the upper left corner, the light comes to a focus, and that's the entrance slit to the spectrograph. Then once the light comes to a focus after the slit, it then diverges. So you can see that diverging beam of light coming down to the lower right corner where there's this collimating mirror. And the collimating mirror has got a curved ground in it such that it takes that diverging beam of light and turns it into a parallel beam of light. And then that is directed to an shell grating, which is effectively the same as a prism for our point of view. And then it goes through these cross-dispersing prisms and then back to this camera at the back end. And then there's a CCD detector, the same sort of detector in your cell phone, except the CCDs that astronomers use cost $100,000 and have to be kept in an evacuated dewar with liquid nitrogen. It would be a little bit heavy to carry around in your cell phone. Okay, so the outcome of an shell spectrograph looks something like this. You see all these stripes of light. The human eye can basically see from about 4,000 angstroms in the blue to about 7,000 angstroms in the red. That's the optical region. And what this does is it chops the light up into about 100 angstrom chunks, and each one of those stripes is about 100 angstroms. And you can imagine cutting through the black dividing lines and taking each of these strips of light and taping it to the one below it, so you had a full wraparound. So what the gorgeous thing about the shell is, by cutting up the spectra into these chunks, you can fit them all onto a single CCD. So for this technique to work, a lot of things had to be invented. CCDs had to be invented, computer speed had to dramatically increase, disk space storage had to dramatically increase, and then there's a ton of work that went into optical design to invent these things. So if you look at any one of these stripes of light, like towards the middle in the yellow, you see there's one order that has two really broad dark lines. That's the sodium doublet. All those other dark lines that you see interrupting the spectra, those are the signature of various other elements. In the case of sun-like stars, most of them are iron, but there's nickel, there's calcium, there's every other element there. And you can learn an enormous amount about a star from these things. You can learn its chemical composition, you can learn its temperature, you can learn its surface pressure, and the truth is, we don't care about any of that. What's important for us is that those little dark lines serve as wavelength markers. And what we're doing is we're looking for those to move back and forth. That's the Doppler shift. So if they move to the left, they're going to shorter wavelength. That means the star is approaching us. If they move to the right, they're going to longer wavelength and the star is receding from us. The problem is that historically, astronomers could measure this Doppler shift to a precision of plus or minus 300 meters a second. Jupiter kicks the sun by about 10 meters a second. So if your effect is 10 meters a second and your error is 300 meters a second, you're never going to detect anything. So this is where we came in at this point to try to develop a much more precise technique.
Thank you for joining us. You have been watching Dr. Paul Butler discussing how planets make the stars they orbit wobble. For more information on the Origins Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Butler will discuss how he pioneered the detection of that stellar wobble. Now, back to the talk.
One of the things I really like to do in these talks is put up photos of some of my closest collaborators and some of the most important people in this field. Steve Vogt, I've been working with Steve since the 1980s. I had a little bit more hair back then. Steve is the guy who really invented modern Echelle spectroscopy. He designed and built the original Echelle spectrometer at Lick Observatory in California, where we found 5 of the first 6 known planets. He then built the high-res spectrometer at Keck, which has found several hundred planets. And most recently, he built the automated planet-finding spectrometer, also at Lick. I always like to say, if not for Steve, I'd be a cab driver or something right now. You know, I literally stand on Steve Vogt's shoulders. So the one thing that we added to all of this is an iodine absorption cell. So the absorption cell is just a little Pyrex cylinder. It's about the size of a Campbell soup can, about 4 inches by 2 inches. And it's filled with only about 1/1000th of an atmosphere worth of iodine. It turns out iodine has only one stable isotope, which makes life much easier. And it absorbs extremely strongly. So, you know, over something that's only 4 inches long and it's only 1/1000th of an atmosphere, you get this beautiful purple haze. And what we do is we mount this iodine cell directly in front of the entrance slit to the spectrometer. So the starlight goes through the iodine cell before it enters the spectrometer. So now the starlight carries both the stellar information and the iodine information. And it's the iodine information that gives us the wavelength of what's happening. So like I said before, errors in the old days were plus or minus 300 meters a second. And by using the information embedded from the iodine cell, that's embedded before the spectrometer, we can remove all of the effects of the spectrometer and back out precision to, these days, to about 1 meter a second. The one thing that we have to do with every iodine cell is we have to calibrate it. We need to have what I call the sacred spectrum of that iodine cell. We need it at a resolution of 1,000,000 and a signal to noise of 1,000. We need a spectrum so good that God could hardly have a better spectrum of that iodine cell. So we take these cells to these incredibly fancy spectrometers called Fourier transform spectrometers. This one is the biggest in the world. It's at the National Institutes of Standards and Technology in Gaithersburg, Maryland, about 20 miles north of DC. And that's Gillian Nave, who runs the atomic spectroscopy lab there. These spectrometers are used primarily by atomic physicists and solar physicists because they need a whole lot of light to work. So in this case, that thing that looks kind of greenish there in the middle, that's actually an iodine cell that we're calibrating, and that's this incredibly bright beam of light that we need to use to illuminate it. So this is the point where I should say, okay, there's going to be a quiz at the end of the program. So this is what our data ends up looking like. That red stuff at the top. So first of all, let me tell you what this is. This is wavelength. This is about 2 angstroms of wavelength. Remember, the human eye sees about 3,000 angstroms. This is a very teeny piece of what the human eye could see. The red at the top is iodine, as observed with the Fourier transform spectrometer, the sacred iodine. And it looks like noise. It looks like grass. But every gidgee there, every divot is real. And then below it in white, that's what a typical sun-like star looks like over 2 angstroms. So now you can see these stellar lines. And then at the bottom, the dots are an actual observation from Lick Observatory. And you can see most of the places where there are stellar lines. You can see the stellar line in the observation, and over here as well. But then over here, there's a place where there's a gidgee in the observation, but there's nothing in the star. That's entirely due to iodine. So what we do is we build a complete model of the observation in which we get the wavelength scale from the iodine. We model the point spread function, the variable smearing function of the spectrometer from the iodine, and we get the Doppler shift of the star. And back in the old days, we got to 3 meters a second with this. And currently, we're doing about 1 meter a second. I'll show you some examples later. So enough about all of that. Let's talk about some of the fun stuff, the science. With this technique, what would the solar system look like? So this shows you that. This is 1960 through 2020. Back when we first generated this figure around 1990, we couldn't imagine that we would ever get to near 2020. And this figure is going to be out of date in a couple of years, so I've got to use it as much as possible until then. And what you see is the velocity going up and down over the 60 years. And to first order, you see a repeating period every 12 years that looks sinusoidal, like a smooth S shape. That's Jupiter. Jupiter is the dominant planet in the solar system. You can, to first order, describe the solar system as consisting of the sun, Jupiter, and some garbage. But you'll notice the high points of these peaks, they go low, high, low, high, low, high. The peaks are being modulated. That's Saturn. So Saturn takes 29 years to orbit the sun, and whereas Jupiter kicks the sun with an amplitude of about plus or minus 10 meters a second, Saturn kicks the sun by about plus or minus 3 meters a second, and basically nothing else in the solar system is detectable. So what you learn is you immediately get the orbital period. You literally can just read it off the graph. And then you get the amplitude, and combining the amplitude and the period to give you the orbital mass, or the planetary mass. So like I said before, you go back just, 21, 22 years ago, there were no known extrasolar planets. This is 51 Peg. This is the very first known extrasolar planet. This was initially discovered by the great Swiss team of Michel Mayor and Didier Queloz in October of 1995. They announced this at a meeting in Europe around the end of the first week of October. And we heard about it right away. We weren't at the meeting, but we were in the astronomy grapevine. But almost nobody else heard about it because there was almost no publicity. Later, when I talked to writers and so on from newspapers and magazines, they said the problem is that virtually every year or two for the past half century, somebody's announced the first planet ever, and the only thing they all had in common was that they were all wrong. And so they were quite cautious about this. And also, this is a very bizarre planet, because you can see this is the first month of data we took. And again, you can read the orbital period right off this thing. It's about 4 days. So this is about a half a Jupiter mass in a 4-day orbit. Nobody had ever heard of such a thing. We now blithely say hot Jupiters, but at that time, this was crazy talk. This was just nutty. So about a week later, we happened to have 4 nights at Lick Observatory. And that's this data right here, just that first bit. And we observed it very hard. We observed it multiple times a night. One of our huge problems at that time was computational power. A bright star typically takes about 5 minutes to observe, but it was taking about 6 computer hours to analyze it. So we had 8 years of data at that point, for which we had mostly not analyzed any of it. We were working really hard both to improve our reduction precision and also to try to figure out how to speed things up so that we could just get caught up. But because this was a single star that we cared about and we threw all of our resources at it, we were able to finish this thing. In fact, I remember very clearly this observing run, this dot right here, at the end of this first set of dots, we took that on a Sunday morning, and then the sun rose. So Lick Observatory is about a 2-hour drive from Berkeley, so we drove back to Berkeley dead tired and crashed. And we met back in the office that night about midnight. And we got this data, and it was like, holy cow, this was right. This was the real thing. And we put out a little figure of that first 4 days on at that time, the brand new World Wide Web. And it circled the world, and about 3 or 4 days later, our telephone started ringing, and it rang for about 6 straight months. And it was kind of exciting, right? You know, because up until that time, you know, I was sort of living in a basement room and people shoving Cheetos and Diet Cokes under the door. On the other hand, it got to be really annoying because I had 8 years of data to reduce that I suddenly desperately had to get. For us, this was a great thing because suddenly the field became very hot, and research groups all over Berkeley would just lend us their computers. They'd say, look, we just took possession of this fancy computer, but we don't need it right away, and if you guys want to use it for a few months, that's fine. And over a month or two, we built up an armada of about 20 computers, and it took us 6 months to reduce that 8 years of data, and 5 planets immediately popped out. So one of the other really cool things about these hot Jupiters is you can draw the whole system to scale on a piece of paper. A Jupiter-like planet is about 1/10 the diameter of its host star, and it orbits something like about 10 or 12 radii away from the star. So the whole thing fits on a nice single piece of paper. You can't do that with the solar system. So another one of the really early planets to pop out is this crazy thing. This is actually around a nearby sun-like star, and in fact, of the 9,000 stars in the Bright Star catalog, this star is the most like the sun. If you were to take a spectrum of the star and put it on top of the sun spectrum, you could not tell them apart. And like the sun, it's got a big planet. You can see this thing with your eyeball, again, an 800-day period, a little over 2 years. Amplitude of about plus or minus 50 meters a second. So it's something like about 2 Jupiter masses. So okay, that all seems reasonable. The problem with this thing is the shape of the orbit. Remember, the previous orbits we've seen have all had this nice smooth F shape to them. But this looks like a saw blade. That's because this orbit is not circular. So prior to the discovery of planets, everybody knew that all planetary systems look just like our own. And by everybody, I mean not just the science fiction producers and science fiction writers, but all of the smartest astrophysicists who had ever lived were all convinced that the solar system was the most typical planetary system ever. And what we found in this case and in the hot Jupiter cases is, in fact, things like the solar system are incredibly rare. So to show you what these orbits would look like, if you overlaid them on top of the solar system, you see you've got this giant 2 Jupiter mass planet, and its orbit is so eccentric that for part of the orbit it would go inside of the orbit of Venus, and for most of the orbit it would be outside of Mars. So that would be really bad for life in this system. If the sun had a planet like this, we wouldn't be here, right? I mean, we would have been bounced out of the system by this giant gravitational bowling ball. So this came up time after time as in the early days of planets. We were finding hot Jupiters, we were finding eccentric planets. We found very little that was even the least bit reminiscent of the solar system. And one of the things I like to remember is, from this experience, is when you have only a single example of something and you're trying to extrapolate from there, that's actually, you're in a worse case than if you had no example. Because if you've got that single example, you've got blinders on and you can't even imagine anything else. So back in these days, you find 1 or 2 giant planets and you'd make the cover of Time magazine. And you can see here how dated this is. Clinton rises. So over the first decade of this business, our goal was to get to 3 meters a second. Remember, prior to that, nobody had done better than about 15 meters a second. And prior to that, nobody had done better than 300 meters a second. So we wanted to get to 3 meters a second. And we began discovering more and more giant planets. We began discovering these bizarre hot Jupiters. We began discovering these eccentric planets. But our goal was to find things more like the Earth. That's always the goal in this business. It's kind of like the spy business. In the spy business, you want your gadgets to be smaller and smaller. And it's the same in extrasolar planets. You want your planets to be smaller and smaller. So we've been working very hard over the last 20 years to improve our precision to 1 meter a second. Already we see some of the benefits of that. I'll talk about super Earths here in a minute and potentially habitable planets. And then hopefully in the next decade or two, we'll move on to even more exciting things and hopefully ending up with direct imaging. One of the problems at this level is the stars themselves. So it would be wonderful if stars were like billiard balls. You know, if there just was some solid surface and the light came out from there and that was that. But stars are these, million-mile across gas balls that are heated from underneath, and they're roiling and broiling, and they've got upwellings and downdrafts. They have pulsations, they have spots. They rotate, so these spots rotate in and out of your field of view, and it can affect all of these measurements. One of the ways that there's this problem is the so-called 5-minute oscillation. So it's known that the sun oscillates on a 5-minute scale. And when I was in grad school, they told me that the amplitude of the solar oscillation was about 25 centimeters a second, so like about that much. So I thought, okay, that's fine, who cares? We're never going to get to that level, and it's just below anything that we're interested in. It turns out that statement is only partially true. Averaged over time, the sun's oscillation is only about 25 centimeters a second. But at any given interval for an hour or two, the major modes that are pulsating in the star can beat constructively. And so this is Alpha Cent A, a very sun-like star in the nearest stellar system in the sky. And we caught this when the major modes are beating constructively, and you don't even need some fancy mathematical device to read the period there. It's 7 minutes. You can just see it going up and down every 7 minutes. And the amplitude's about 2 meters a second. So we have to worry about this 5-minute oscillation. We have to worry about the rotational period of the star. We have to worry about the convection time scale. That's the sort of the boiling time scale of the sun's atmosphere, which is typically an hour or two. We have to worry about the magnetic cycle. And the truth is, most of these problems haven't been solved.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Paul Butler. Dr. Butler and his team are currently monitoring over 1,700 stars to look for planets. In the second part of our talk, we learned about the instruments that Dr. Butler uses to look for planet-induced stellar wobbles. In our final segment, Dr. Butler will talk about the planets he has discovered and the future of planet finding. Now, back to our talk.
So nature keeps throwing us screwballs. We keep finding planets that we never even imagined would exist. And this is one of the very first super-Earths. So getting to finding much smaller planets means you've got to beat your measurement errors down. But it turns out nature is really cruel and vicious. If you imagine just a single small planet going around the star, you'd have this repeating signal, and life would be good. But nature almost never does that. What nature typically does in these systems is she throws in a whole bunch of planets that all cause roughly the same amount of Doppler wobble. So they're all beating against each other. And so this is 61 Ver, and this is data that we took with the Anglo-Australian telescope in Australia. I was a staff astronomer there back in the late 90s. And we would observe the star typically 3 or 4 times a year. So you get a point here, a point here, a point here. We knew something was going on. We had absolutely no idea what was going on. Finally, in 2007, the Time Allocation Committee gave us 48 straight nights. That had never happened before. And we picked about 20 stars, bright stars, and we tried to observe them every single night. So each one of those points is one night of data. You'll see a few gaps. That's weather. On top of everything else, Mother Nature throws weather at you. Rough world, huh? But once we had this data, we could immediately disentangle the signal. We could now suddenly see it. There is this period that you see that has the 4-day period goes up and down with an amplitude of about plus or minus 2 or 3 meters a second. So that's a 5 Earth mass planet in a 4-day orbit around the star. So 5 Earth masses is probably rocky. So this is one of the very, very first super Earths that were found. Super Earths are typically thought to be roughly 2 to 10 Earth masses, and the composition isn't entirely known. But if they're this close to the star, they're probably rocky. It would be hard for this thing to hang on to a gassy atmosphere. But on top of it, you see the whole thing is modulated. There's this 1-month signal. That's about a Neptune mass. And then if you take even longer data string, it turns out there is yet a third planet in this system, 61 Ver D, which is about 2 Neptune masses. So the problem becomes that the planets, the signal of the planets beat, and that's why this thing goes up and down. And to disentangle this just requires a huge amount of data, and often taken in high cadence, like that previous plot where you observe every single night. And we'll see a classic example of that towards the end of this talk. Here's another example of just how hard this game is. This is one of the very first potentially habitable planets. There's 2 data sets here. The blue data set is the harps data set from the Swiss group. This is a telescope operated in Chile. And the red data is from Keck. This is data that we took. In each case, there is about 120 observations. So there's a total of about 240 observations. And that's what it took to disentangle this thing. It's got planets at 3.15 days, 5.7 days, 12.9 days, 37 days, 67 days, and 433 days. And this is around one of these so-called nearby M dwarfs, or red dwarf stars. These are stars that typically have about 1/10 to 1/2 the mass of the sun, but they have very low luminosity. They typically only put out about 1% about as much light as the sun does. So these are very faint stars. And because they're so faint, the so-called habitable zone is much closer to the star. The habitable zone, and it's like, for us, the habitable zone, 1-year orbit. That's the magic spot. That's what we like. For these red dwarf stars, the habitable zone is typically like 10 to 30 days. So by habitable zone, because astronomers, they go talk about habitable zone, I think everybody knows what they're talking about. It doesn't mean there's life there. Okay, we have no idea if there's life there. All it means is it's the right distance from the star that it could potentially have liquid water on the surface. That's all that means. So you've put a stop here, but I think that was covered in the last one, so we'll just skip. So back to this, this M dwarf. So you see the sun, and you see this M dwarf Gliese 581, and then this blue band here is the so-called habitable zone. And that planet in a 37-day orbit falls right into it. So we announced this in 2010. This thing is also about 5 Earth masses, so it was one of the very first potentially habitable planets to emerge. Our goal, other than finding nifty planets, is to beat down measurement error. In fact, I would say every day I wake up, I don't think about finding planets. I think about how can I make my measurement error smaller. That's all I care about. Planets will follow. The most important tool that we have right now for this is the Magellan Planet Finding Spectrometer. So this is at Las Campanas in Chile. This is the Carnegie Observatory site. It's about 8,000 feet. And it's probably got the best natural seeing of any observatory in the world. By that I mean the image of a star on a typical night is smaller than anywhere else at any other observatory. And on the right here you see those 2 funny looking domes. Those are the 2 6.5 meter Magellan telescopes. Carnegie owns a 50% share of them. And then Harvard has a 20% share, and then MIT, Michigan, and Arizona each have a 10% share. So that's the main reason that Carnegie is able to hire astronomers. We have a lot of telescope time. So the most important thing in this business, other than a big telescope, and in fact the most important thing in this business, even including a big telescope, is your spectrometer. That's what you're making your measurements from. 2 of my closest collaborators are Steve Schuckman here on the right and Jeff Crane. They designed and built the planet finding spectrometer at Magellan. And this photo is actually taken at the Carnegie Observatories building in Pasadena. And you can't see it just off the camera shot to the right is the Magellan planet finding spectrometer. This is in November of 2009, just before we shipped it to Chile. And I said to them, I want to get light in here. I want to see some spectra because I got to start writing software to reduce it. So Shuck here grabs a mirror and he's reflecting sunlight from the window into the spectrometer so that we can get some spectra so I can start writing software. So the thing, what I really love about this picture is, in Shuck's case, if you become enough of a guru in whatever you're doing, in this case instrument building, you can actually become one with your instrument. So here is what the planet finding spectrometer looks like. It's actually mounted on the side of the telescope. So the primary is actually just behind this thing. And it's been opened up so that you can take a look inside of it. Previous spectrometers that we had used had all been general purpose shell spectrometers. They had been designed for every astronomer who's doing everything from the most distant quasar to the nearest moon in the solar system and everything in between. They all have different goals. They're looking at different wavelength regions. They want different resolution. And these general purpose shells, by definition, have to be flexible. So that's terrible if you want to make nothing but precision velocity measurements. If all you want to make is precision velocity measurements, you don't want anything in your spectrograph to ever change or move. You want precision. So the previous spectrometers had been very large. Not as large as this room, but as large as like a living room. They're typically steel I-beams sunk in concrete with big optics hanging off of them. And the rooms were so large that you couldn't temperature control them. You just got what you got. So this is a super clever design in which the light is actually coming into the spectrometer near where that gold thing is. That's actually the CCD. And then it's bent. It travels all the way through all the optics. The shell is in that black can on the far right. And then it goes through all of those same optics again and comes back to that CCD. So it makes a double pass through the optics. So this had not been done before. And because you're making a double pass through the optics, you can make the instrument much, much smaller. And then the instrument is encased in 4-inch thick styrofoam. for insulation. So the front panel is taken off here for you to see it, but that almost never happens. So years go by without us taking the panel off, and we heat this whole thing to about 27 degrees C, which is what, about 80 degrees or so. Because even though we're in the Atacama Desert, at 8,000 feet, it never gets to 80 degrees. So now we have this super precise spectrometer. Nothing ever changes. There's nothing you can move in it, and it's always temperature controlled. Here's an example of the incredible improvement you can get with much better instrumentation. This is a known planet that we had found from a previous spectrometer at Magellan. The triangles are the data from the old spectrometer, and you can see the scatter is about 7 meters a second. And then the black dots are the new data from the planet finding spectrometer, and the scatter collapses to 1 meter a second. Better precision means you can find smaller planets. So that's what it's all about. So here's I'll show you an example, and we're moving towards the end of this talk here. This is a planet actually we discovered with the Anglo-Australian telescope back around 2009. This is another one of these little M-dwarf stars. And this planet was kind of nifty because it's got a 9-year orbital period. The eccentricity is mild. It's almost circular. So this is a Jupiter-like planet in a more or less circular orbit. It's one of the only known systems like this where it's an M-dwarf with a planet like Jupiter that we can recognize. But you can see the scatter here is 6 meters a second, and that's all we could do. It's a 4-meter telescope. It's a crappy old spectrometer. That's all we can do. So here is the same system. The green points are from the Anglo-Australian telescope, so that's the discovery data, and it's good enough to discover the system, but that's all you can get out of it. The red data is from harps, and the blue data is from our PFS, and you can now immediately see how things collapse down, and the detection is much easier. But it turns out you can now look for residuals in this data fit and see if there's anything else in the system. And it turns out there is. Hiding in this system, there is this 33-day planet. There's no hope you would ever see it in the Anglo-Australian data, but in the HARPS and PFS data, it comes out, and this thing is about 3 or 4 Earth masses. So another very early super Earth. So this is Guillaume Anglada. He is another one of my very close collaborators, a guy I've been working with very, very closely for the last several years. I think he was just named this last week in Time magazine as one of the 100 most influential people on the planet Earth. So I had this slide in here before he became famous. So Guillaume and I started working several years ago to try to unlock the HARPS velocities. The HARPS is part of the European Southern Observatory, so it's a governmental organization that basically includes virtually all of Western Europe. So the data has to be made public. But if you went to the archive and you grabbed the velocities for any given star, it was of almost no value because the star would have been observed for different projects. They would have had different templates. There would be offsets. There's no information. There's no way to recover it. So Guillaume basically single-handedly, with just a teeny bit of help from me, wrote a code that could recover the HARPS velocities from the spectra itself and actually produce higher precision than the HARPS team does. So he began with this new code to grab HARPS data for a lot of stars, including Proxima Centauri. And when he did this, he looked at the archival Proxima Centauri data. He saw a hint of several signals in the 10 to 20 day region, which for Proxima is in the habitable zone. So, and it's the nearest star in the sky. So, you know, that's pretty exciting. But Guillaume is very cautious, and he wanted to see the signal in more than one telescope and with more than one technique. I mean, when you can see a signal in multiple telescopes with multiple techniques, then you know it's real, because these signals are becoming very small. So he recovered the data from another group called the uvas group that were using an 8-meter telescope in Chile and using an iodine cell. So that's this data here. So the data in red is the original uvas data. And in this case, the scatter is about 3.3 meters a second, and the ultimate signal of Proxima Centauri ends up being 1.5 meters a second, and he couldn't see it. You can't see the data. You can't see the signal in this data. So Guillaume asked me to clean it up, and I spent 6 weeks writing a brand new reduction package specifically for this. And that produces the blue data. And now the scatter is reduced to about 2.3 meters a second. More recently, I've gotten it down to 2.0 meters a second. And now you can see the signal. So the next slide is going to focus on this data set right here, because it was observed almost every night for 16 straight nights. And again, the red is the original uvas data, and the blue is after I had re-reduced it. And now you can see there is a hint of a signal at 11 days. And Guillaume used all of this to get a big allocation of harps time. Starting in January of last year, he got a half an hour at the end of every single night for 2 straight months, and observed it at very high cadence nightly for 2 straight months. And the end result is this. These circular dots that show this 11-day signal very nicely, that's from the high cadence run. The triangles are the uvas data, and the square boxes are the harps data that he had previously harvested. So one of the things that you learn here is the older harps data is just like the new harps data, same telescope, same spectrograph, same reduction package, and yet there's much more scatter. That's because when you observe a star occasionally over 10 years, in addition to your own measurement errors, you've got all the stuff going on in the star. You've got magnetic cycles in the star, you've got rotation of the star, you've got all these other things going on that are throwing in extra noise. And when you observe something in high cadence every night for a few weeks or a few months, all of these other sources of error collapse down. So that's why you get this dramatically better data. And this kind of, this is a line through a bunch of points. It looks kind of boring, but it got the cover of Nature last August. This is kind of a benchmark because this is by definition the nearest star in the sky. And there are these various programs now like Starshot where they are now actually targeting Proxima Centauri because of this discovery. They actually want to send something there. They're talking about something like a sophisticated cell phone that they could send in maybe 30 or 40 years that would beam us back some image or something as it went flying by. So it's kind of wild, 400 years ago, people speculating about this business getting burned at the stake. And now we are maybe 30 or 40 years from having the technology to actually fling something at these stars and to look at these planets. So let me just finish up by showing just a few slides giving a hint of what the future might be. And I say a hint because I have no ability to predict the future. If I could, I'd be worth so much money that you all would never see me. So this is a cartoon of something called the Terrestrial Planet Finder, which is a plan NASA had going back more than 10 years ago. And the idea is that you would put 4 or more biggish telescopes in the sky, like maybe 4-meter-sized telescopes, and that they would each collect the light from the star, and then they would send it to a combiner. That's this thing that's off to the right. And this would be an interferometer. So there was a question here about interferometry. And so this is one of the main ways that people are thinking about how you might actually find a planet, because even with a space-based telescope, you still got the problem that the planet's right next to the star, and the star is 1 billion times brighter if you're lucky. But in an interferometer, you can combine the wavelength of light out of phase. So that at the center, where the star is producing all the light, if you combine the light out of phase, they all cancel. And so here in the center, you see that dark band. And then there are these stripes. These come directly out of interferometry. And in these stripes, you might have a hope now of detecting the planet. So they show the little simulation of the planet off to the side. The other way to find planets is going to just be brute force and it's going to take 30-meter telescopes on the ground and dramatic advances in adaptive optics. I mean, the sort of stuff that the Air Force already does, but astronomy is always at least a generation behind the Air Force in terms of advanced adaptive optics. That's because they have real money. So let me just end up where these things always end up, with the Drake equation. The Drake equation sort of historically has been the equation which outlines our ignorance. The goal of the Drake equation is to estimate the number of communicating civilizations in our galaxy, because they're the only ones we have any hope of communicating with. And you get this by multiplying the rate of formation of suitable stars. So that's a number that's actually been known reasonably well for 50 years. And then every other factor after that has been totally unknown prior to 20 years ago. We didn't know what fraction of stars had planets. We didn't know the number of Earth-like stars per planetary system. We still don't know the fraction of life where planets develop, and the final one, the fraction where intelligent life develops. And by the way, in this equation, intelligence doesn't mean that you've produced Da Vinci or Shakespeare or Michelangelo. Those things are all nice, but those things cannot communicate between the stars. You become intelligent when you can build a radio telescope that's big enough to send a signal across the stars. So by that definition, humanity's only been intelligent like basically since the end of World War II. And of course, the final thing, the fraction, the lifetime of the communicating civilization, because we became intelligent at the end of World War II, but Lord knows we may not be here in 50 years with all the other problems going on. So what's happened in the last 20 years is we've answered the second question here, the fraction of stars with planets. The fraction of stars with planets is 100%. I mean, there might be an oddball or two, but virtually every star has planets. The number of systems with an Earth-like planet in the system. Right now, both the Kepler transit mission and ground-based Doppler velocities have come to the exact same conclusion from totally different sides. It appears that about 1/3 of all stars, about 30% of stars, have potentially habitable planets. Stars with potentially habitable planets are a dime a dozen. They're everywhere. So we've answered, in 20 years, we've answered 2 questions. That's not bad. And we've left questions here for young people, grad students, and people younger than that. They have something to chew on. I mean, wouldn't it be just terrible as a grad student if all of these things were already known? What would you do? So we've come full circle, and I'll end there. And I think that was pretty close to an hour. So thank you very much.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.